Welcome to the webinar. My name is Mike Medoff with Exida, and I'm going to be talking about the Security Development Lifecycle today and how this process can be used to help improve security of products and to reduce the overall vulnerabilities found in products and systems today. Just a little background on Exida before we get started on the detailed part. So Exida is a company that was founded around the year 2000, and we're mostly based in the US and in Europe, but as you can see we do have other locations around the world. And the company was founded with the main goal of trying to help companies, both suppliers and users of products, comply with the emerging functional safety standards such as IEC 61508 and IEC 61511. So essentially, when these standards came out, it was difficult for companies to comply, and Exida felt that this was an area that we could really help lead people and explain how these standards work and supply tools and consulting and training. And so really the goal of the company was really to help improve functional safety and improve safety around the world. Over the years, we've expanded that mission to include other things that are very closely related to safety, such as cybersecurity. As you know, a cyber incident very well could lead to a dangerous situation in a plant today. And alarm management, another area where dealing with the plethora of alarms that can occur during an emergency situation is also very important to safety. So our roots are in the automation and process industries. But we've also expanded it into automotive and nuclear. Automotive essentially started following very similar functional safety standards, and so that was an area that we naturally kind of grew into just with our experience in functional safety. So we work with suppliers, we work with designers, we work with end users. And so the way we deliver our mission to kind of help in these fields is we do consulting. We supply a number of engineering tools to help do things such as calculate failure rates and make sure you have reliable systems with low probability of failure on demands that can show that you meet the right SIL level and security level. We do product certification for both cybersecurity and functional safety. We do training. We have a lot of reference materials, including a number of books we've written on the topics. As well as a lot of failure rate data that helps in the area of functional safety. And we also offer professional certification programs, like personal certifications, in both functional safety and cybersecurity. So our certification program is essentially, we're accredited by ANSI to do certifications, and we essentially certify products, systems, components, personnel, as well as processes. And so what we're going to be talking about today, the Security Development Lifecycle, is really a process, and you can have that certified, companies can have that process certified. That process is also very well part of product certifications, and we'll talk about that as well. And as I said, we've come up with a number of reference materials where we essentially document. Our philosophy is that we want to share our knowledge with the world. We want to explain how we do things, and so we try to publish a number of books that essentially explain our processes that we go through to help other people learn and understand that. And as I mentioned, we also have a number of tools in the area of functional safety and cybersecurity. Some of these tools can be used by suppliers, some can be used by end users, and they're in the area of functional safety, cybersecurity, and alarm rationalization. Okay, so my name, once again, is Mike Medoff. Some background on me is I spent about 20 years in the product development field, developing software for control systems and safety PLCs with a company called More Products, which eventually was purchased by Siemens. Today I work mostly with suppliers to help them make their processes and products compliant with functional safety and cybersecurity standards. From the cybersecurity point of view, I'm the leader of the ISA 99 task group, working group 4, task group 6, that's developing the 62443 4-1 standard. which is essentially security, basically product development lifecycle requirements. So it's the standard that's really closely related to the topic we're going to be talking about today, which is how to develop products securely, building security into your normal product development lifecycle. I'm a voting member of the ISA 99 committee. I've written a book on the development process, how to develop products for functional safety compliant with 61508. I'm also very involved in the ISA Security Institute, so I'm on the technical steering committee for them. And for those of you who are not familiar, this is a group that's within the ISA that was formed to help facilitate and define cybersecurity certification programs. And so I'm on that group and have been a developer of some of their certification programs, specifically the SDLA certification is one area where I've been heavily involved, as well as the EDSA. And I'm a lead auditor for many cybersecurity and functional safety certifications here at Exida. So what we're going to talk about today is what is the SDL, what is the security development lifecycle, how does it help prevent security attacks, how does it fit in with the current standardization efforts. There are efforts going on in this area, and SDL is a key part of some of the 62443 series of cybersecurity standards. Then we'll talk about a little bit about how do you implement an SDL, what are the major parts of an SDL, and then if you're an asset owner or an end user, how can you ensure your suppliers are using an SDL, and if you're a supplier, how can you show your customers that you're using an SDL. So SDL stands for Security Development Lifecycle, and essentially it's a process that's used when developing software and hardware to reduce the likelihood of security vulnerabilities in that product. So initially the SDL really was mostly focused on software, but during the development of the IEC 62443 standards, we got a lot of feedback that really a lot of these processes and practices that we're applying for software can apply to hardware as well. And so we spent a lot of time trying to put some examples in and make sure that the standard could apply to both. So it seems to apply a little bit more to software, but if you're putting security functions in hardware, it certainly applies there as well. It's based on a study of root causes of security vulnerabilities. So we've had a large number of security vulnerabilities reported on products in the world today, and there's been a lot of study of those to figure out what are the root causes and how do we prevent them. And that's really where the SDL came from, is trying to figure out how to prevent these security vulnerabilities from occurring in the first place. And an important aspect of it is it evolves over time as new types of security vulnerabilities are uncovered. So security is very much not a static area. It's a very fast-moving field. And so there's things we're doing in the security lifecycle today that are the best practices today, and that will change. Even 6 months or a year from now, there might be new or different things that need to be included. And so that's an important part of the security development lifecycle, is to be ready for and include that, prepared for that change. So just a little background on where does this fit in overall security. Where does the security development lifecycle fit in? If you look at what are the enablers or kind of the things that lead to cybersecurity incidents or security breaches, one is like just simply the insufficient features in an application or a system. So you could have a system that doesn't require any passwords, or that doesn't require strong passwords, or it doesn't encrypt data, so it's sending data in the clear, and it becomes very easy for someone to monitor that data using something like Wireshark and figure out how to send similar messages to that system. So there's really a certain number of security features you want to put into a product to secure it. And a lot of times that's what people think about when they think about product security. It's just putting those features into place. But another part of it is the end users. You can put these features into place, but a lot of times the end users might not use them. Security often can be difficult to use, and so it's a common issue that people will bypass it just because of the difficulty in place. So it's very important to realize that security, just buying secure products or products that have great security features, is not enough to secure your system. The users have to know how to use it and agree to use it in a secure fashion, even though there's going to be some cost to them. Social engineering is another common way, where somebody calls you up and said they're from the IT department, for example, and they want your password. Or the big issue today that we see a lot of is phishing emails, where click on this link and it could be anything from your Verizon bill is late to any other types of issues that come from that. But then the fourth area, or the other area that causes cybersecurity incidents, is vulnerabilities in software. So even if you have software that is essentially has all the correct security features, has very strong encryption, strong passwords, the users are using these features, they've been trained against social engineering, those are kind of things that we think we can control in security. But even if you're doing all that, there's a lot of vulnerabilities that have just been found in the software itself. And as a user of software, these seemingly are beyond your control. The only thing you can seem to do about these is to make sure your system is patched, which especially in the area of industrial automation and control systems is very difficult and costly, and often we just can't patch the systems or keep up with the patches in this area. So this is really what this webinar is focused on, is how do we reduce these vulnerabilities in software, the area that we sometimes feel that we can't control. And that's exactly what the Security Development Lifecycle was developed for, to try to reduce and eliminate these in the first place. So the Security Development Lifecycle was actually pioneered by Microsoft. Given their exposure and the number of security vulnerabilities that have been found in their product, they really were one of the companies that really had to face this security issue the most, or before a lot of other people have. And so they obviously had to try to find better ways to secure their products, and they did do that. They did improve security, and they felt it was important to share with people what they did, and so they essentially wrote several books on the topic describing the security development lifecycle, and that really has become, their work has become the basis for what is being included in standards today, and what has been continuing to develop. It has certainly developed more than just what they started with, but they have been a major contributor in this area. And it has been created in response to real vulnerabilities, analyzing the causes and trying to come up with ways to prevent them from occurring. There's a number of attack patterns that have been documented and categorized, and once we understand these attack patterns, we can understand how to protect against them. And so the SDL has been developed against these known to handle these known attack patterns. But also, a key part of it, as I mentioned earlier, was there's going to be new attack patterns that are invented and discovered, and this is happening at a very quick rate. And so as that happens, an important aspect of the SDL is to be able to adapt to that. So there are some standardization efforts, as I mentioned, that are going on related to SDL. Key among them is ISA IEC 62443 series of standards. So these series of standards are developed around industrial automation and control system security, and so they include all the different aspects of covering the different ways to prevent security incidents. So this 2-1 standard covers asset owners' roles and responsibilities. What do the end users have to do to secure their systems? Asset owners usually or often will hire integrators or maintenance personnel to develop and maintain their systems, and there's a standard 2-4 that essentially talks about how those groups, the processes they need to put in place to ensure security. The 3-2 standard talks about overall cyber risk assessment and system design. So cybersecurity is a big issue to tackle, and so risk assessment is a very important part of it, because it may be difficult to secure everything 100%. So it's very important to figure out what are the highest risk areas and secure them first and secure them the most. The 3-3 standard talks about system security capabilities. So these are the security features that your systems or products have. 4-2 is kind of a derived standard from 3-3 that talks about the security capabilities or features of products, and it's very closely aligned with 3-3. And then, so finally, then the 4-1 standard is about the product development lifecycle. And so this is a very important part of the overall series of standards. This often maybe not thought about, as I said, because it's done in the background, and people that are maintaining systems might not always be thinking about this issue. But it's a really important issue that if we can develop products from the get-go, including security throughout the life cycle, we can make a big effect in reducing the number of vulnerabilities, and therefore reducing the ability for attacks to occur and reducing the cost and frequency of patching systems. So this just kind of shows the overall 62443 series. As you can see, some of these standards are published, some are still in development, some are still planned, but they essentially break into general, there's some policies and procedures, which these are really like the procedures that an end user or asset owner would use, and then there's the system standards, 3-2 and 3-3, and then the component level standards, such as 4-1 and 4-2. One thing to point out about this arrangement, though, is that the 4-1 standard was developed for product development or component development, but really it actually can also apply and should apply to system development. So in the ISA Security Institute, we actually have applied a lot of the 4-1 requirements to a system security certification, which was developed by ISASecure, called the SSA, System Security Assurance. So that's an important thing. Even though it's under component, it should be also considered for system development. In terms of where we are with these standards, the 4-1 standard recently passed a vote by the ISA to become an ISA standard, and it's currently out for vote for the IEC as an international standard. So that vote is due by the end of July, and then at that point we'll find out if 4-1 will become an approved international standard. So it's kind of halfway there by having the ISA, by passing the ISA vote. So the 4-1 is broken into these 8 different practices. There's the security management side of things, which is essentially assuring that you plan security activities, and this is also related to having a fundamental good software development process in place. So if you look at security vulnerabilities in a product, really they are just a class of bugs in software, a class of software bugs. Any security vulnerability is something that the software really shouldn't be doing. Either it wasn't specified well enough, or it was just a bug, straight bug in the code. And so therefore, by reducing bugs in software, you can reduce vulnerabilities. And so it's very important to have a good general software engineering, software development process in place, similar to the kind of process you would put in place for functional safety, or for something like CMMI, the capability maturity model, if you're familiar with that. Just trying to improve the overall quality of your software really has a direct relationship to the security of your software, and it's a foundation upon which the whole security lifecycle is built upon. The other aspect of security management, the planning of security activities, kind of seems kind of basic, but it's really important that you can't just add security in at the end is kind of the key. You need to plan it, and you need to have time allocated for it and people to work on it. And if you don't plan it up front, then usually we find that it won't occur. Specification of security requirements is where you define the security features of your product. So those are the features that are important to have in your product, and so from a process point of view, it's very important that you have clear requirements on how they should work, and those are easily understood and testable, etc. The secure by design practice is essentially designing security into the product, and a very important phase. As I said, if you don't do that up front, it's very difficult to add it onto a product at the end. Security implementation is, so now that when you're actually developing the product, you're actually implementing it. This is really mostly like the coding of it. What are the things you need to do at that point to ensure security? A lot of security vulnerabilities are caused by just coding errors, and some of them are not errors by your software developers. They're actually coding errors in the languages and the libraries that we use and the tools that we use. And so those are very important to understand those causes, and there are a lot of ways to minimize those today that we'll talk about in more detail. Security validation, verification, validation testing. So just like any product, you want to test its features, you want to test a product's security features, but security testing also includes a lot of negative testing. In other words, rather than just testing that the security features work out correctly, try to test what happens when unexpected inputs come into the system. Because essentially, that's what almost all security vulnerabilities come from. Users try to send unexpected inputs, and if the program can't handle them, that often leads or may lead to a security vulnerability. Security defect management is the whole process of being able to respond to security vulnerabilities, whether they're reported to you externally from a customer or from a security researcher, for example, or as well as security vulnerabilities that are found throughout this process. So because we're including security throughout the whole life cycle, vulnerabilities can be found at any stage, including requirements, design, testing, coding, etc. And so you really want to manage them all in a similar way. And that's a key part of the life cycle. Security update management is managing security patches. So specifically, as a product, you may include other products or components that have patches, and so you need to make sure that you include those patches. And then you may also depend on other components, such as the operating system, for example. And in the industrial automation world, it's very important that you can show and demonstrate that your software is compatible with the with changes to the operating system or with other dependent components. End users are very hesitant to install operating system patches without knowing that the control system or some of the key control products are still going to work with that. And so that's become an important, and it's been included as an important part of the life cycle, is to make sure you're testing and telling the world that you're compatible with these various different patches. And then the last practice is security guidelines, and this is essentially like a contract between the product developer and the user. So the product developer can't really ensure the system is secure just by itself. There's certain steps the product manufacturer, supplier has to take, but there's also other steps that the user has to take to complete that whole secure system. So a lot of times people think you just use these secure products and you're going to have a secure system. That's not at all true. The user has a very big role in this, and so the security guidelines is where the product supplier can make it very clear what role the user needs to have for these particular products. All right, so the security management process, we'll talk a little bit about each of these processes in more detail. It was put in place to ensure that security is considered throughout the life cycle, and to make sure you plan for it, and to make sure you have good basic software engineering principles as part of your development process. So it includes things like project management, having a good development life cycle model. A very important aspect of it, though, is security training and competence. Many of the systems that we have today have been developed 10, 20 years ago, and even new systems that come out today often include a lot of code from older systems that were developed in the past. And so when many of these systems were developed, a lot of these techniques were not understood and certainly not practiced. So it's very important that the developers working on these systems understand the cause of security vulnerabilities and understand how to address them. In classic software, computer science training, software development training in colleges, etc., many people, many engineers, software developers were not trained on these techniques. They were essentially just trained on how to develop software, or how to develop different technologies, how to get it to work right. But there wasn't a lot of consideration to security. That is definitely changing today, and the schools are definitely considering and teaching that more. But today, on a typical development staff, you may have a number of developers that just are not familiar with the causes of these vulnerabilities and what they need to do to prevent them. So that security training is a real key part of this, that all of your developers need to have an understanding of the cause of security vulnerabilities and how to fix them. Some of your security developers probably need to have a much better understanding. Maybe they're your security leaders, but everyone has to have at least some basic understanding. All right, so the practice for specification of security requirements is where you're defining the security features of the product. Another key aspect of that, though, is you will specify what we call the security context for that product. And this is a very important aspect where you're essentially trying to define what is the environment that that product will be used in from a security point of view. You know, is this going to be something that's put in a locked cabinet in a locked room with no connection to any networks, or is it something that's going to be a web server that's going to be facing out to the internet and can be accessed by anonymous users over the internet? So these different environments definitely add requirements to the product, and so it's very important to understand what that environment is going to be and define that when you're defining the requirements. Even if you are, as we'll talk about in more detail, even if you are in a very secure environment, that doesn't mean you don't have to consider security, but it might mean it's not, you don't have to do nearly as much as you might for a system that is much more exposed. Also, during the specification of security requirements, it's very important to understand that the requirements are well understood and can be validated or tested. Oftentimes, once you write a requirement, it's a really good idea to start coming up with a test plan right away, even before it's implemented. Oftentimes, when you try to do that, you'll find it's hard to come up with a test plan because the requirement's not clear enough. And if that's the case, it's probably also not clear enough for your developers. So this is a very good way to find weaknesses or lack of clarity in requirements early on, is by trying to develop a test plan to validate those requirements. Okay, so secure by design is really one of the key areas that will take place in developing a secure product. And so there's a number of areas that are part of that. One is threat modeling, and so this is where you try to model what real-world threats, security threats, are out there that would apply to this product, and then you try to ensure, once you've identified what those threats are, you try to ensure that you have ways to mitigate them, at least the ones that are the highest risk. You might define some threats that are not very high risk, and you might not worry about those so much, but the ones that are high risk, in order to protect against it, you need to know what those threats are, and so that's really what the threat modeling concept is about. Attack surface reduction is another very important step where you can make significant improvements in security without having to redesign a lot about a product. It's essentially the attack surface is essentially the different paths of attack, if you can think of, for a product, and oftentimes you can reduce those paths simply by doing things like taking a feature that's always enabled and disabling it by default. You might have certain features in your system that maybe only 10% of your customers use, but those features expose the system to more potential vulnerabilities or potential paths of attack. And if only 10% of your users are using it and you disable it, then by default, then that essentially eliminates that attack path for 90% of your users that aren't using it. Defense in depth is an important concept we'll talk about, and it needs to be considered in design, which is related to essentially having layers of protection, and that each layer needs to protect itself. So even if you have that system that's not connected to the network and is in a locked cabinet, you can't completely ignore security. You have to think about ways that can possibly be bypassed, and you need to build some level of security into even a product like that. Secure design principles are very important to have as part of your development process. These are best practices that you apply, and this is one of the areas where the process can handle change that I've spoken about earlier. We know that there's going to be new security attack patterns developed over time and discovered, and therefore there'll be new security best practices put in place, and that's not something that you really can easily capture in a standard, because a standard might only be updated every 5 to 10 years, whereas these attack patterns might change every year or more frequently. So having these security design principles in the process, best practices, if you will, and then also the process of updating them periodically is very important as well. And then security design review is another very important part about design. Typically, we've seen in the best organizations, as I mentioned, everyone needs to know a little bit about, or, all the developers need to know something about security, need to understand the basics. But the best practices we've seen is to have some senior lead security engineers on the software development team that really understand in depth the causes of vulnerabilities, and that they're involved in reviewing every design for those such issues. All right, so just talk about a little bit of these in a little more detail. So threat modeling is essentially a systematic approach to understanding the complexity of a system and identifying threats and vulnerabilities, essentially by looking at the system as an adversary's perspective. So you kind of look at the system a little bit like a black box, and you say, okay, what are the paths of entry? What are the assets in the system? It's very important to understand that the assets are the things that an attacker would desire to attack or gain control of. So like in a financial system, that would be something like social security numbers or credit card numbers, but in an industrial automation and control system, it might be information about how a process is done. So it could be secret information about intellectual property about a process that is in place, or it really could be one of the big draws to an attacker in an industrial automation and control system is essentially the ability to have a physical impact on things. So a control system is controlling physical parts of the plant, and that's something that is very desirable for an attacker to be able to take control of. And so the process is really to analyze these assets, analyze entryways into the system, and identify based on that what are the threats to the system. And once you have that list of threats, then that is then an input to say what are the highest risk threats that we need to worry about. So you want to apply risk to all of them, and then how do we mitigate or prevent attackers from exploiting these threats or taking advantage, implementing these threats. So the threat model is very important because without that, it's unclear what you should protect against. So it's really where you define the important things to protect against. So threat modeling process might look something like this. Create models of the system. Typically, most people that do threat modeling will create data flow diagrams, which show how data flows in and out of the system and between parts of the system, because that's usually the paths where attacks occur. Identify trust boundaries. So a trust boundary is where data crosses from one trust level to another. So in other words, you might have some places where any remote anonymous user might be able to send messages to a device. But once that message crosses a firewall, for example, then okay, that's a more trusted area. Now this might be an area where it might be in a locked room where people need a higher level of authority to get into. So if somebody goes through the GUI, the graphical user interface, that might be a higher trust level, for example, than something that comes from completely outside the plant. So you really need to understand what these trust boundaries are within the system, and define them. So anytime that trust level changes, you define that trust boundary, and those are the very important places where you need to look at the data coming in from a lower trust level and be skeptical and not trust it, and do some validation to make sure that it's safe and acceptable. You're going to identify entry points, data flows in the system as part of the threat modeling, and document assumptions and external dependencies. That's also a very important part because a lot of times things you assume or things you depend on are the very things that are sources of vulnerabilities. In other words, you might be depending on something such as an operating system for security, but if that operating system has vulnerabilities, that might completely compromise your product, for example. So you need to understand exactly what those dependencies are and consider threats of what if they get compromised, how do you protect against that. You're going to identify assets and then consequences of those assets being compromised, as that will help identify the risk, and will really help identify what the most likely attacks are. So from going through this step, you'll be able to identify threats, decompose the threats, in other words, figure out what does a attacker need to do to exploit this threat. Usually it's not just one thing. It usually might be 2 or 3 or 4 different steps they have to go through or that have to occur in order for an attack to succeed. And so you want to understand that, because sometimes just eliminating one of those steps can be the way to mitigate the threat. And then you're going to assess the risk of each threat. Then you're going to identify any existing mitigations, because you might have things in place already in your product. But then you're going to say, what are the remaining potential vulnerabilities you have in your product where you don't have mitigations in place? And then you're going to use that to identify the highest risk items which you will address first. Okay, so attack surface reduction is the other key area as part of design. And the attack surface is designed as basically the code, interfaces, services, protocols available to all users. So think of any code that can run on a product as something that an attacker might try to get to run somehow, might send some message or somehow initiate that code running. And attackers will try to use that code, exploit that code to essentially accomplish whatever their goals are in compromising the system. So all code, has some level of risk associated with it, and if you identify the code that has the highest level of risk and make it so it doesn't even run in most cases, as example I gave previously, just disabling a certain feature that most people don't use, and they would have to enable it in order for it to use. Essentially, that code is not available to run, and it's not an attack path for that attacker. So attack surface reduction is kind of saying, yeah, we know there's going to be vulnerabilities in the code. We're going to take care of them in other places, but this is one place where you can get a big bang for your buck and potentially reduce the attack paths, and therefore reduce the chance of a successful attack significantly with just a little bit of work. That doesn't mean you don't have to try to eliminate the other vulnerabilities in the code, because you're still going to have the 10% of your users, for example, that use that code. But it definitely can add significant gains for relatively low cost, so very high return on investment. So when you're doing attack surface reduction, essentially you focus on reducing the amount of code that executes by default, so disabling features that aren't commonly used, restricting the scope of who can access the code. So this is, maybe only certain users can access certain features, restricting the scope of which identities can access code, so only certain roles. Maybe only operators can access certain code, and then maybe only maintenance personnel cannot access other code. And that way, if an attacker, is able to steal someone's identity, an operator's identity, they only get a subset. They only get access to a subset of the features that they want to try to exploit. And then reducing the privilege of the code. If you have code that runs at a high privilege, that's from a microprocessor operating system point of view, that's very desirable for an attacker. If he can take control of that code, he might be able to take control of the whole operating system. Okay, so defense in depth is another very important concept during design. It's an approach based on the idea that you're going to have layers of protection, and any one of those layers may and probably will be defeated at some point. You kind of, defense in depth, you make that assumption that other layers will be defeated. And so therefore you don't rely, you don't say just because there's another layer out there, I don't have to worry about security. Yet just because there's a firewall in front of me, I'm not going to put anything into security. Each layer, you really want to make it difficult for the attackers to compromise. And the more layers you have that are difficult to compromise, the more difficult it's going to be for a successful attack to occur. So this kind of, if you design with this method in mind, it forces attackers to have to break through and bypass multiple layers, so it's not like they just break one thing and they're successful. Each layer should really be designed, think about, to protect itself if all other layers have been defeated. Okay, security design best practices. So these are things that you would make as part of your process that you'd adhere to during design, and architectural as well as detailed design. And so there's kind of a series of kind of timeless security best practices that will probably always apply. And so in the standards, we tried to put these as like a minimum set of best practices that should be followed. But then there's also going to be a whole another set of best practices that are changing over time. And so this is really the part of the process where you allow and expect change in the security environment, and you really want to periodically update your best practices so that you're prepared when new attacks vectors or new attack patterns are found. Once somebody has defined a good best practice to defend against that, you can put that into place right away. So these are, things, such as separation of privilege, least privilege, making sure that each user only has access to the part of the system they need to have access to. Those types of common things. I won't be able to get into any more detail on that during this webinar, but those are the types of issues that are included there. Okay, so secure implementation is really what you're doing when you're in the software side, when you're coding things. So a very important part of that is static code analysis. There's a number of what we call potentially exploitable implementation or coding constructs out there. So some of these are as simple as functions, like if, many of the vulnerabilities out there today are due to people that are using the C and C++ languages. There's a number of functions in those languages that essentially don't do any checking on buffer size. So in other words, you might be copying data, maybe a message received, from a user or from an external entity, and maybe you have 100 bytes of storage for that message, but the attacker is going to send you a message saying it's 2,000 bytes of data, and seems kind of obvious. Yeah, you shouldn't copy 2,000 bytes of data when you have a 100-byte buffer, but there's a whole bunch of functions built into the C and C++ languages that didn't check against that, and so that was really the cause of some buffer overflows, many buffer overflows in the past. When this problem was realized, new functions were created in the C and C++ languages that addressed these issues, but then the attackers found vulnerabilities in these new functions. So then a second generation of new functions was created, and I think at this point they now have created secure functions. But you may have a lot of legacy code in your products and may still be using some of these older functions, and so static analysis tools are really important to be able to run it on your code, find these cases, and fix them and eliminate those problems in your code. So this, very least, should be part of something. Any new code you write, you run all the time, and you also should be going back and looking at your current existing code base. And you might not be able to fix all the issues at once, because you might have, you might have millions of lines of code, but you should definitely be putting something in place where you try to steadily improve that with the goal of eventually fixing all the code. So another big thing in the implementation phase is validation of inputs that cross the trust boundary. So you have inputs that are coming from some unknown or untrusted source. You don't want to just accept that message and trust it. A common example in the industrial automation and control is control systems typically have configuration programs that configure, what the control algorithms are running, what particular function blocks are running, etc. And when many of these were created, there's a special format. The messages come from these configuration programs, and so anything that came from the configuration program was trusted by the controllers because they had to. They have to get a configuration. They have to trust this information. But if this information is not encrypted, for example, then it becomes very easy for an attacker to study the messages that get sent down and mimic them or replay them. And essentially, that's a way to change the configuration of the controller, which can really allow the attacker to have significant control on what he wants to accomplish. So really, you need to not trust that data. You need to validate it somehow, authenticate it, have some kind of encryption. Those sort of things need to be put in place, and that's an important part of the implementation phase. Verification and validation testing includes security requirements testing, so actually testing your security features. Threat mitigation testing, this is essentially ensuring that things you put in place to mitigate specific threats work properly. General vulnerability testing is kind of a way to find vulnerabilities in your software. And penetration testing is another way to find vulnerabilities in the software. General vulnerability testing is more of a repeatable kind of testing you can do. Penetration testing is more of an expert testing, and it's very much based on the ability of the attacker or the person doing the penetration testing. But if you have a good penetration tester, they can find things that you might not find using the tools that you would use for general vulnerability testing. So the general vulnerability testing consists of abuse case testing, where you're essentially trying to abuse the system rather than entering expected input. You're expecting unexpected values. Kind of a subset of this is malformed or unexpected input testing. This is often called fuzz testing. So this is very common practice done on communication protocols, where you'll fuzz them, or you'll send in unexpected values. Maybe a message comes in that's supposed to be 100 bytes in length, kind of to the example I was using before, and you change that length field to be, say, it's 4,000 bytes. So it'll copy a lot more data than it should. So fuzz testing is very important. In the 62443 standards, we say that anything that parses external data across a trust boundary should have some kind of fuzz testing on it. And so that would apply to communications. It could also apply to, like, reading files. You might have files that are just stored on disk, so somebody could access those files and corrupt them in a way that is essentially an attack when those files are opened. This kind of testing also can be done at the GUI level. You might have places where you enter values in a GUI, and you want to consider doing that there as well. But there's a number of tools that are available for doing it for the communication side, and it would really be very difficult to do that testing without tools, either developing them yourselves or buying some commercially available tools, because you essentially want to test thousands or maybe even millions of test cases when you're doing fuzz testing. Attack surface analysis, there are some tools out there, especially in the Windows platform, that will analyze your attack surface and give you pointers on how you can minimize it. Known vulnerability scanning is, there's a large database of known vulnerabilities in operating systems and components that might be used in your products, and this allows you to scan and find those known vulnerabilities in your products and eliminate them before you release them. Software composition analysis on binary executable files. A lot of software today includes open source code or third-party code, and that may have vulnerabilities that you might not realize when you use that code. And so software composition analysis or binary scanners essentially can find those problems. They can find vulnerabilities known vulnerabilities in such code. And then dynamic runtime resource management testing is kind of a way to test the software while it's running and look for things like memory leaks and other things that could lead to security vulnerabilities. Security update management, as I mentioned before, is making sure that you test patches from components that are used in your product, as well as things that you depend on, such as operating systems. And you essentially want to test those and document that and supply your users, tell your users that you've tested it and you found these to be compatible, as that often users in the industrial control system will not want to install those patches until they have that feedback. The security guidelines, you kind of look at security as responsibility of everybody. So the product has their responsibility, the system integrators have a responsibility, the users have a responsibility, and so you can't just develop a secure product and install it and be secure. And so this is, in the security guidelines, is where the product developer states, here's what we've done, but here's what we need you to do as our user. And so it's almost, you can look at it as like the contract between the product developer and the user. If you really want to have a secure system, you need to use that secure product and use it per this contract. So this kind of shows that like everyone has kind of a piece of the pie, if you will, in securing a system. And then the part that applies to users is something that can be defined in those security guidelines. So the security guidelines will talk about, one of the important things is how do you secure the system. A lot of times we want a system to be secure by default, but there's optional configuration settings and you need to that make a system more or less secure, and just for practical reasons we need that. And so you want to try to make that simple so you can secure the system easily. but if not, you need to supply security tools that allow people to run a tool that says, hey, this is what you need to do to completely secure the system. You need to change these particular settings. Also, your assumptions, like where the system is going to be located, and what kind of things the user needs to do. Maybe they need to have a firewall or a demilitarized zone all the time with the system. Those things would also go in the security guidelines. So if you're an end user and you want to ensure that your suppliers are using a security development lifecycle, hopefully I've explained some of the value of it here, and you really realize that you really want to be using suppliers that are using these practices. So obviously you need to ask them questions. The big basic question is, are they using a security development lifecycle? And then, is it compliant with any standards such as 62443? I know some people might say they're compliant with the Microsoft Security Development Lifecycle. Some way of compliance or measuring it against something is an important thing to look for. Another key aspect is how long have they been using this process. Many of these products, as I said, have been around for many years, and it's not likely or maybe even possible that they've been using these processes for an entire length of some of these products. But what we want to make sure is that A, they're using it going forward, and B, they're not only just using it for new development, they're going back to their legacy code and trying to continuously improve that with the goal of eventually getting that up to speed. That's not going to happen overnight. We understand that that's a very expensive process, but they need to at least go for a steady improvement of that existing code. You obviously can audit your customers or ask them for a third-party audit to do that. So now, if you are a supplier and you are using an SDL and you want to show your users who are concerned about security about that, you obviously should supply them, tell them what you're doing. You could allow them to audit your process. That could get expensive, obviously, if you have multiple customers that want to audit your process. So one of the things we provide is a third-party certification where we'll come in and look at your process and issue a report and a certificate if it's compliant. And so we have two types we look at. We look at the ISASecure Security Development Lifecycle Assurance certification, and then we also will do a certification to the 4-1 standard. And so these are very closely related. To understand the differences is the SDLA developed by the ISA Security Institute was intended to be based on IEC 62443, but the problem is there was a delay in the development of 62443, so the ISA Security Institute took the initiative and they developed the SDLA first before 62443 was available. And in fact, the SDLA was then given to the ISA 99 committee and became version 1 of 62443-4-1. But the two have diverged a lot since then. The 4-1 has had a lot of review from international, different IEC committees around the world, and so because it's been subject to a lot more review, it's evolved. And so they've diverged, but they still, the words have changed a lot. Maybe like 90% of the words have changed. But the content is still very closely aligned. I would say, both of them really talk about a lot of the same concepts that I talked about today are in both of them. And if you comply with one, it's very close to complying with both. And that's oftentimes what we do. When we do a certification, we'll certify people to both. Now, once 4-1 passes the IEC vote, which we're hopeful will be in the next month or two, they will be merged again, and then the SDLA will be completely compliant with it. And so, but for now, we recommend people take a look. If they're doing an SDLA, they take a look at 4-1 as well, so they're prepared for that. Okay, so a couple other quick things is, so you can have your process certified to the SDL. The SDL is also a key part of product and system certifications. So you can see here, the ISA Security Institute has the Embedded Device Security Assurance certification. So this is an embedded product certification. And that consists of three main things. So the Security Development Lifecycle, looking at the process used to develop that product. A functional security assessment, looking at the security features in that product. And a communications robustness testing. This is doing some of the, mostly fuzz testing, and communications flooding, denial of service testing, for example. So there's really several aspects that we look at when we do a product certification. But in either case, getting the process to be compliant is really kind of the first step I would recommend for any supplier, because you're going to need that, and it takes a little bit of time to put that in place and to apply it to products. So similarly, the system certification consists of similar three components: robustness testing, security functions, and the security lifecycle. All right, so I think I want to leave a few minutes for questions. I guess I'll just say one last thing I'll just go through is, if you're looking to have your process certified, this is a little bit what the process would look like. We would come in, we would do an optional gap analysis. So if you have a good SDL in place, this might not be necessary. If you're really not sure where you are, we would come in and say, here's the gaps between what you're currently doing and the standard. Then once you address those gaps, we would analyze your procedures. So this is a paper exercise where we would look at your development procedures and compare them to the standard. And we create what's called a security case, which documents, how those procedures are compliant with the standard and any gaps or any issues that we find there. Then there's an on-site audit where we now take a look at, okay, we know your process or your paper procedures are compliant. In the on-site audit, we look at what you're really doing. Are you following those procedures, and how are you doing that, and is that compliant? We would typically do that for each site that's part of a certification. So some of the certifications we've done cover multiple sites, although some sites, the on-site audit can be remote. It doesn't have to be actually on-site for every single one. Address any issues that come up in the audit, and then we would issue a certificate which is valid for 3 years. So essentially, it has a 3-year valid point, because we want to, after 3 years, we want to kind of make sure that you're still doing it. Things have changed over this time. I'm sure your process changes over that time, and we kind of want to verify that you're still following it and that any changes in your process are still compliant. Okay, so I have a little bit of time for questions. If anyone has them, I'll answer them now. If we run out of time or people can't stay on, I can certainly try to get to questions. I can respond afterwards as well. I don't know if there's a spot. I actually do not see any questions right now, so I'm not sure if any have been asked. I'm just not seeing them, or let's see. All right. Well, I don't see any questions right now, so I'm not sure if there are any questions that I'm not seeing. I will certainly try to respond after the meeting with an email, and certainly feel free to send me an email if you have any questions. I don't know that I had my email address on here, but it's mmedoff@exida.com. Let's see. I'll just take that here. All right. I want to thank everyone for attending, and I hope this information was useful to you, and thank you very much.